In this video, we're going to solve a second-order linear equation in the case of resonant forcing. So suppose we're given a differential equation. So we can see that this is second order, non-homogeneous, linear. It's also undamped because there's no dy dt term. And we can see that it has sinusoidal forcing. In this case, there's a cosine term. So by looking at this forcing, we can see that the forcing frequency is 5 over 2 pi. So this can be read directly off of what the forcing is. So in order to solve this, we want to first solve the associated homogeneous problem. D squared y dt squared plus 25y equals 0. So as always, we solve this by guessing a solution of the form e to the lambda t, which gives us a characteristic polynomial. And that characteristic polynomial is lambda squared plus 25 equals 0, which means lambda equals plus or minus 5i. So you can get that by applying the quadratic formula to this. So at this point, we can see the natural frequency is gotten from the imaginary part of the root of the characteristic equation. So the natural frequency is 5 over 2 pi. So if we have a checklist in our heads about whether or not this harmonic oscillator is going to experience resonance, we have that the forcing frequency is equal to the natural frequency, and there's no damping. So this is the case in which we would expect resonance to occur. So we're going to keep that in the back of our minds, and that's going to come up again later. So moving on from this, once we have the roots of the characteristic equation, we get a perfectly good complex solution to the associated homogeneous equation. So roots of the characteristic equation give us a solution to the associated homogeneous equation. And this solution has the following form: e to the root of the characteristic equation times t. So you can just pick either plus or minus 5i and put it here. So this is a perfectly good complex solution to this associated homogeneous equation. But we want real solutions, so what we can do is we can expand this out using Euler's formula. And it turns out that if you have a complex valued solution to a real differential equation, that means its real part and imaginary part are also solutions to this equation. So any linear combination of these guys is also a solution. And that means it turns out k1 cos 5t plus k2 sine 5t is the general solution to this associated homogeneous equation. So we've solved the associated homogeneous problem. So next up, we need to find a particular solution to this non-homogeneous problem. Since the forcing is sinusoidal, what we're going to do here is we're going to complexify this problem. And this makes the solution quicker. So what we're going to do is we're going to declare the complexified version of the non-homogeneous problem, the complexified version of the non-homogeneous problem, to be 3e to the 5it as the forcing. So this is a different differential equation than this one, and we're going to solve this guy. So we're going to look for solutions of this guy. And when we find such a solution, call it y dt because c was already taken. We're going to take the real part of y dt. So why is that? Because our forcing, 3 cos 5t, is the real part of this forcing, 3e to the 5it. So if we get a complex valued solution to this differential equation, we can take the real part of that complex valued solution and we'll get a real valued solution to this differential equation. So we're going to take the real part of y dt when we find it. So this is certainly different than what we did with yc of t when we were solving the associated homogeneous problem. So you want to make sure there's a distinction in your own head between this process and what we did earlier. So how do we solve for y d of t? How do we solve this different? How do we find a particular solution to this differential equation? So we're going to guess, or if you prefer, we're going to employ the method of undetermined coefficients. Since the forcing here is exponential, we might guess alpha times a similar exponential. But, so I mean, this is a fine guess. However, we are in the resonant case, as we decided earlier. So if you guess something like this, it's going to turn out not to work. It's going to turn out that there's no such alpha where this is a particular solution to this differential equation. So instead, we're going to go straight to the time-tested second guess, which is guess that y dt is alpha t e to the 5it. So we're just going to put a t on it. So we're going to plug this into both sides of the complexified differential equation, and then we're going to find what alpha works. So what we're going to do is we're going to have the second derivative of this y d of t plus 25 times this y d of t. That equals 3e to the 5it. So we're going to skip all this differentiation for now. There's a lot of product rule involved because we have a function of t times a function of t. But what we're going to get eventually is 5I alpha e to the 5it plus 5I alpha e to the 5it minus 25 alpha e to the 5it plus 25 alpha e to the 5it. And that's going to equal 3e to the 5it. So simplifying this, we get 10I alpha e to the 5it equals 3e to the 5it. And then we can cancel out these e to the 5it's. And then you have alpha equals 3 over 10I. And if you multiply the top and bottom by the complex conjugate of the bottom and simplify, what we get is this is minus 3 over 10I. So this is the value that alpha must take on if this is to be a solution to the complexified differential equation. So at the end of the day, we get that y d of t is equal to alpha, sorry, not alpha because we just figured out what alpha is. Y d of t is minus 3/10 I t e to the 5it. So this is our particular solution to the complexified differential equation. So at this point, we've found our solution to the associated homogeneous equation, and we have a particular solution to the complexified differential equation. Now, if we remember, what we wanted to do to this is we wanted to take the real part of it, and that'll give us a particular solution to this equation. So in order to find the real part of this, we're going to use Euler's formula on e to the 5it and get cos 5t plus I sine 5t. So we can see this first term when we distribute is going to be imaginary. It's going to have an I in it. And the second term, I times I is minus 1, cancels out with that negative. So we have 3/10 t sine 5t. And this is the real part that we were looking for. So a particular solution to this differential equation is 3/10 t sine 5t. So at this point, we are, in fact, done because we can add yht to yp of t, and we'll get our general solution. So this is how you solve second-order linear equation with sinusoidal forcing in the resonant case.